Hey guys, today we will be learning about how sound waves, whether it is from your guardian yelling in the morning or the music coming from your earbuds, gets to your ear, travels through the external middle and inner ear, and ends up in the brain to be interpreted. Our ears, speaking to the individuals who don't have some of the disorders we will be talking about momentarily, or should I say, rapping about momentarily, can determine pitch, location, as well as loudness. Our talented ears have the ability to split different complex sounds into a variety of frequencies and tones. So now that we have a little understanding of what our ear is capable of, let's go over how these sounds, whether pleasant or aggravating, get to our ears. The first step would be sound waves get funneled into the external ear, which consists of the pinna, external auditory canal, and the eardrum. Once it gets to this spot, the eardrum receives the waves and begins to vibrate. So from the eardrum, it goes to the malleus, then to the incus, and then to the last bone in the trio, the stapes. After these good vibrations get to the stapes, next is something not so routine. So far, the sound has come in and good vibrations have gone from the eardrum to the stapes. Now that the stapes is vibrating, it pushes on the oval window, located directly behind it. And the pressure that is put on the oval window causes the air-filled middle ear, which again is the three small bones, the malleus, incus, and stapes, and the oval window, which is attached to the fluid-filled inner ear, which is just the cochlea, to separate. This then leads to the vibrations in the inner ear. Now we are at the one and only cochlea. It is snail-shaped and plays a huge role in the way we hear sounds. The cochlea's job is to break down the different frequencies that get sent to it. Essentially, each part of the cochlea is responsible for a certain frequency. Therefore, if there's a high frequency, a certain part of the cochlea vibrates, and if there's a low frequency, another part of the cochlea vibrates. It's actually quite similar to a piano. When a certain string is pulled, it causes a different frequency, whether it's high or low. Covering the cochlea are hair cells. These hair cells pick up the vibrations, good vibrations, that have been sent to the cochlea and turn them into electrical signals. The hair cells sit on many different parts of the cochlear basilar membrane and work in tandem with it so that if there's a very low sound that comes in, only a certain portion of hairs, the ones that work to low sounds, will send the electrical signal and this would work for whatever frequency comes in. These electrical signals go to the auditory nerve, which carries them off to the brain through the medulla oblongata and midbrain. The part of the brain that is responsible for the way we perceive sound is the temporal lobe. In this particular section is the superior temporal gyrus. Say that 10 times fast. That has the auditory cortex in it. It can be split into three different sections: the primary, secondary, and tertiary auditory cortex. The primary cortex is the part that is sensitive to different frequencies. The secondary cortex can process melodies, rhythm, and patterns. And lastly, the tertiary auditory cortex blends all these things together to configure the songs we hear. The auditory cortex neurons respond to tones of different frequencies. They are also capable of understanding different mixtures of tones. For example, certain neurons will respond to a pure sound, like a recorder, depending on who's playing of course, or a complex sound like a guitar. These neurons can also combine the information that they acquire and recognize words or instruments like the ones listed above. The auditory brain, which is the term used to refer to the part of the brain responsible for sound, receives signals and while interpreting them, begins reflex or conscious perception. The auditory brain also has the ability in a way to instruct the cochlea to pick up and emphasize a particular sound. This is useful when having a conversation with someone. Say you're at an event with a lot of people around you talking. Your brain can instruct your cochlea to focus on the conversation you're having with someone while blocking out the other noises in the background. There are 3 different levels at which the brain interprets sound. First is the reflex. This means the sound we perceive causes us to move physically. For example, getting scared and then jumping would be our ears sending us a message all the way up to our auditory brain, and its response is to react physically. Second, as mentioned above, is the auditory cortex, where sound is interpreted by various levels of pitch, frequency, and with the help of other parts of the brain, interpreted. Third, the other part of our brain plays a significant part in the way we all perceive sound. The ability to recognize sound is linked to whatever memory we have associated with it. Also, once this sound is recognized or now being stored in the brain, other parts of the brain help out to make the right response. The way the brain interprets sound differs when compared to being awake and asleep. When you are awake, all three levels are intact and fully functioning. An example of this would be when Casey and myself went up and started talking. When you heard our voices, you began to listen, perhaps you even turned your head to see what the ruckus was. This would be the reflex part. You recognizing the sound of my voice due to how charming it sounds, or the sound of Casey's voice due to how annoying it sounds, would be linked to the frequency and pitch of our voices, also linked to the memory part associated with hearing. And if you were to ask a question, a response would be linked to the third level of sound processing. Now, when we are asleep, this process is not fully complete. The ears are still working, sound travels all the way to the auditory brain, but the part of the brain involved in emotions and memory are inactive, meaning there is no voluntary response or conscious perception. An example of this would be Casey's sleeping and I start singing her lullaby. I don't know why I'm doing it, I just am. This peaceful lullaby is heard, but because she was asleep, tomorrow when I ask, "Did you hear my lullaby, Casey?" she would have no recollection of what happened because at that point in time her brain was inactive. Some things that are interesting about the three different levels at which the brain interprets sound is that even during sleep, a noise that is loud enough can make the inactive part of our brain active again. If the noise is loud enough, of course varying for different people, it becomes conscious and causes a voluntary response. An example of this would be waking up because an alarm clock went off. Another thing that is interesting is that we have the ability to alter the sounds that cause us to wake up. So say you can sleep through a tornado, but now you have a newborn baby and it is essential that you can hear the softest noises the cute newborn can make. This soft noise can cause you to wake up because it has been programmed in your brain that it is an important noise needs to have the inactive parts of your brain active again. I hope you enjoyed this presentation we provided and enjoy the rap coming up.